Hello.
Hey, Erin.
Hey, Erin. How's it going?
It's going. How about you?
Happy morning for you.
You too.
Hey.
Midday.
Well, it's like
Late
10.
morning.
So when you have a 7-month-old, it is like midday at 10 o'clock.
I'm gonna try and share my screen and see if it works.
Yeah, it's perfect. May need to give you access. Or I don't know, Kat, are you the host? No, I'm the host. I don't know. It works.
It works?
I can see it.
Yeah. Perfect.
Great.
Woohoo.
We have about 33 people registered. In my experience, anytime you have to register for something, there's a lot of people, not a lot, but there's usually a handful of people at the end that are like, oh, I didn't realize I had to register. So it might be a little bit more, but as of right now, there's 33 people.
Okay.
And I'm gonna keep people in the waiting room until we're a little bit closer to time. Maybe in a couple minutes, I'll let folks in. I'm gonna start letting people in like 1 or 2 minutes, probably like 1 minute.
Okay.
All right, I'm gonna let the floodgates open. Hi, everybody. We'll get started in just a couple minutes.
Meeting's being recorded, so I can't do any of my usual cursing then. Good morning.
Mike, we record you all the time without you know. So.
Good morning.
Good morning.
Hey, Alan, how's it going, man?
How you doing there, Mike? What
I-
college is that behind you? I never heard of that.
What'd you say?
What college is on all those banners behind you? I didn't know that school.
It's a little tiny school up the road a bit. That's all. Us and 60,000 of our best undergrads there.
Good morning, everyone. We'll get started really soon. Great. Good, everyone. Welcome to our second Maricruz Science Talk. The point of these talks is to highlight the great research going on in the Mid-Atlantic. This session is being recorded. The recording and slides will be posted on the Maricruz website soon. We just ask if you could please keep your cameras off and your microphones muted during the presentation. There will be time for discussion and questions after the presentation. Today we are featuring Dr. Aaron Bever as he talks about the real-time, short-term environmental forecasting of the Chesapeake Bay, setup, uses, and next steps. Dr. Bever received a PhD in marine science from Virginia Institute of Marine Science, College of William and Mary in 2011. He has more than 15 years of experience combining field observations and state-of-the-art 3D hydrodynamic, water quality, sediment transport, and wave modules to better understand coastal and estuarine systems. Most of his work has focused on salinity and turbidity modeling and sediment deposition and dispersal in San Francisco Bay, and also on methods to better estimate and forecast hypoxia in Chesapeake Bay. Take it away, Aaron.
Okay, thanks. So thanks everyone for attending. The focus of this talk is going to be on a operational real-time forecasting system for Chesapeake Bay that we've had running since about February 2017. And if we gave this talk in February 2017, it would be similar but a little bit different, because one of the things that we try and really do is continuously update it and kind of continuously evolve it based on kind of the advancements in the modeling aspect side of it and in response to stakeholder feedback. And so I'm going to summarize kind of the setup of the modeling system, some of the uses, and then some of the next steps that we're planning as kind of a continual improvement and continual advancement in the forecasting system. So as a little background, we can kind of think of three types of forecasts. One is like a long-term forecasts or projections. And if we think of that as hurricanes, we can think of it as with climate change, we expect some parts of the world to have more hurricanes, some parts to have less hurricanes. And it really helps people kind of start to plan on the decadal or the century time frame. Like, how do we plan for the long term? There's a shorter forecasting interval, kind of seasonal. So this would be like, how many hurricanes do we think we're going to have this year?
Hey, Aaron, I'm sorry to interrupt. I'm not sure if you think you're sharing your screen, but we can't see anything.
Okay. I can see it fine. There we go.
There you go. Yeah,
How's that?
perfect.
Okay. So we've got the long-term forecasts here on the top left. That's what we just described. And then you step down to the seasonal forecasts. Like, how bad do we think this hurricane season is going to be? Kind of a shorter term planning. And then eventually we get to where there's a hurricane and you're either in the cone or you're out of the cone. And it really helps kind of plan for that next couple days. And it's these short-term next couple day forecasts is what our Chesapeake Bay forecasting system is focused on. It's really to provide information to help make decisions in the next couple days. It's not looking at, it's June, what am I going to do in August? It's June 9th, what am I going to do June 10th? You're standing at the dock, you're standing in your aquaculture facility, you're about ready to get on a boat and go do field sampling. How does it help us make those kind of day-to-day decisions? And so we've been calling this forecasting system the Chesapeake Bay Environmental Forecast System, or CBEFS. And it's based on an underlying three-dimensional hydrodynamic model. And it's the ROMS Regional Ocean Modeling System and a full biogeochemical model, or the estuarine carbon biogeochemistry model, or ECB. And we run completely automated every night a one-day nowcast, which is essentially yesterday, getting us up to today. It's our best estimate of what conditions are now, and then forecast 2 days out into the future. So what's it look like 2 days from this morning? And then every night there's some post-processing that goes on, and the results are displayed on the internet. And so I haven't checked it yet today, and if we do, it's going to be a bummer because VIM's power is out, I think, as of now and as of last night. So if you go to www.vims.edu/hypoxia, you'll see the web page, and chances are it looks like the web page from yesterday and it hasn't updated today. So generally the forecasts run automated every night and they work very well. There are some instances like today where the power goes out and there's nothing that we can do about that. One of the last ones, a car hit a telephone pole and it was out for a little while. We kind of have to go back in and manually run it by hand. But if you're intrigued, go ahead and go to that website and browse around. And we forecast many different environmental variables. A lot of what's actually run in the model we don't put out there, but we do post-process out a lot of information that's kind of been requested by stakeholders or that we think is interesting. So things like temperature, salinity, dissolved oxygen, pH, alkalinity, omega. And then we also process out the hypoxic volume to look at how much hypoxia there is on any given day and kind of track it throughout the season. This is kind of a schematic just to kind of get ideas around how it works. And some of you may be very familiar with this type of thing and some of you may not. So the first thing that we have to do is get all the input files that the model needs to run both the nowcast of yesterday and the 2-day forecast. And when we initially set this up, one of the things that we did was really leverage what NOAA has already been doing in the Chesapeake Bay. And so this first step is really retrieve CBOF's input. So CBOF's is NOAA's operational model of Chesapeake Bay. And it's used for different uses than what ours is. And so we retrieve what CBOF's used for model input and then reformat it for ChesROM. So kind of reformat it for our model for CBEFs with the E. And then once that's been done, we can run the 3D numerical model, so the hydrodynamics and the biogeochemistry. After that's done, there's a series of checks that's done on file sizes, make sure all the outputs are there and various things. And it sends one email if it was successful, like good job. And then if there ends up being a problem, then there's a whole train of emails that there was a problem. And they all provide kind of the breadcrumb clues as to where the problem was. And then we go back in and run it by hand. So as an example, since the power is out, I don't think the HPCs are running, and I have 0 emails from the forecast this morning. I assume when the power comes back on, like I'll get a whole slew of emails telling me that it didn't work. And then once we do the step that checks that everything worked out right, there's a lot of post-processing that goes on. And so some of this is simply generating the images that are going to be displayed on the web page, and then actually putting those web pages out on the server to be displayed online. We also calculate some variables outside the actual hydrodynamic model, some of the carbonate system variables. And going forward, we're going to be looking at some habitat stuff for maybe possibly for fish or for Vibrio, HABs. And so we'll post-process out those probabilities of occurrence, add those to the NetCDF files that are put out from the hydrodynamic model, and then add those to an online server where they can be downloaded. And so Marcus is putting the forecast on the Chesapeake Bay Oceans Map webpage. And so after we append any variables to the output is part of the post-processing step, then Marcus just grabs that output so that then anything that we want to add, we can add, and then Marcus can just grab that for the Oceans Map webpage and not have to do a bunch of post-processing steps kind of on their end. So the model itself is driven by atmospheric, riverine, and kind of coastal inputs and coastal forcings. We've recently updated to a higher resolution hydrodynamic model, kind of this representation here, at about 600 meters by 600 meters using 20 vertical layers. Oh, I see this slide should be changed a little bit, but for dissolved oxygen, we're running a complex biogeochemical model, the etch-stream carbon biogeochemistry. And in the lower resolution version that we were running a more simplistic one-term respiration rate oxygen model, this SRM, but we've dropped that when we went to this higher resolution model. And then we need river inputs. So we're using forcing from observed gauge data from USGS. And then as I'll talk about a little bit later, we're scaling that to better represent the total freshwater inflows. And for the biogeochemical model, we need nutrients and biogeochemical variables, which aren't provided by the USGS gauge data. And so we're taking those from climatology. For the meteorology, we're using the North American mesoscale model. And since January 2018, that's been a hourly 3-kilometer model. And so it's been fairly high resolution in both space and time. And then at the open boundary, it's being forced with tides, non-tidal water levels, things like coastal surge, wind-driven setup from the ocean and things like that. And then again, for the biogeochemistry variables, we're just using climatological data to force those. And like I said before, when we first set this up, one of the things that made it a little bit easier to set up was that we could leverage what NOAA was already doing. So NOAA was already operationally forecasting water levels and sea nettle probability of occurrence throughout the bay. And so they were doing temperature and salinity and water levels. And they put their input files along with the output files online every day. And so we could simply automate the download of the NOAA CBOFS input files and reformat those for use in our model. So we would get the river freshwater and temperature inflows, open boundary non-tidal water levels, and all of the meteorology that we needed. And initially, this made it very quick to set up because we didn't have to go to all of the individual sources that NOAA was pulling from to get all of this information. It was just all in one place and formatted in a way that's fairly consistent with what we need, because NOAA's running the ROMS model and we were running the ROMS model. So something like meteorology, we could just put together a few of theirs to make a longer time series and go. There was really no reformatting that was needed. And then once we get those reformatted inputs, we append the biogeochemistry onto it because NOAA's not doing any biogeochemistry. And so we really had to add that. And so this table is a little dense, but I kind of wanted to have it in here in case there were questions or something at the end. And it's essentially a summary of what we're using as forcing for the model. Although a lot of it is actually at this point coming from the NOAA files. This is some of the end or some of the starting for where all the data comes from. And so we're using the river inflow from all the major tributaries to the Chesapeake Bay, and then a few of the more minor ones. And like I said, we're using the North American, the NAM hourly 3-kilometer meteorology, which is post 2018. And because, so if I just step through this a little bit, so we're using the tides, and because CBOPS is so focused on water levels, we're actually using 37 tidal harmonics and really trying a lot with the tides. Non-tidal water levels are driven by hourly data, kind of an interpolation between Duck and Ocean City. Salinity and temperature then is from another forecast model. And then biogeochemistry, obviously, from climatology. We've touched on the NAM for the meteorology, but we're also including nitrogen deposition onto the bay as one of the biogeochemistry terms. And that's based on climatology. And so it's spatially constant, but it varies by day based on the paper by Dot et al. From 2018. For river inflows, the discharge is just based on USGS gauge data. I'll get into that a little bit more later too. And then the rivers have a temperature, which is based on either a climatology or a USGS data, however CBOPS is doing it for that river. And then for biogeochemistry from the rivers, we used a watershed model, the dynamic land ecosystem model, to develop climatology for the river inflow biogeochemistry. And for some of those, it's temporally constant. It varies monthly. It kind of varies daily on a seasonal cycle. Some of them are spatially constant. Some of them are spatially variable. It's kind of whatever that makes the most sense for that variable and kind of how it looks out, kind of how it compares from river to river and day to day. So one of the things that we've done is we've put a bit of effort into calibrating the model. And so, I mean, that seems obvious, but we started with a calibrated hydrodynamic biogeochemistry model of the Chesapeake Bay. And then we changed all of the model forcing to the CBOPS forcing. And so one of the things that we've worked at is how do we make the model better while still being true to the CBOPS forcing that we can just retrieve every day to do the forecast. And so essentially the forecast model is using different forcing than the hindcast calibrated model. And so we developed a way to combine all of the 6-hour nowcast inputs from CBOPS into one continuous forcing file. And that allows us to run 2014 through 2017 and then 2018 through 2020 as continuous model runs to see if there's ways that we can tweak the CBOPS forcing to make our model better. And we examine the effect of wind speed and tributary freshwater discharge on model accuracy. So it's one of the kind of the two main things that we looked at recently. And the idea is that wind speed over the Chesapeake Bay in the meteorological products, whether it be NAM or NAR or ERA5, if we just start throwing out acronyms, the wind speed is often lower over the water than the observed wind speed. And if we just use USGS gauge data for the tributaries, we're really likely underestimating the total freshwater inflows to the bay. And so these are kind of two low-hanging fruits. Can we scale the wind speed, or can we scale the tributary inflows to make the model better? And the answer is yes. And so we developed a simple scaling based on comparing the USGS gauge data to the watershed, the total freshwater inflows predicted by the watershed model. And this is kind of a summary of the results. So the figure on the left is essentially the baseline run. This is using the CBOF's inputs just as they come. And the figure in the center is using the scaled discharge. So all we're doing is scaling the freshwater discharge generally up to account for kind of any flows below the gauge station and things like that. And the figure on the right is a target diagram, and it has the baseline model run. So what comes from NOAA, the scaled inflows, scaled wind speed, and then if we combine scaled inflows and scaled wind. And the idea here is that each one of the dots is a different year, color coded by the scenario. And then the shape is just kind of representative that it's a different year from 2014 to 2017. And the closer to the center of the bullseye, the more accurate the model is. And so we can see that generally for salinity, for bottom salinity, the light blue, the baseline, is the farthest from the center. So the baseline is probably the least accurate in this case. And then if we scale the inflows, we scale the freshwater discharge, that moves the dots closer to the center. It essentially reduces the bias in the model. The model's biased high. We can see that by the scatter plot on the left. The best fit line is nearly 1-to-1, but it's shifted up. This center scatter plot there, you can see the best fit line is now not quite 1-to-1, but it's kind of centered right on the 1-to-1 line, and the bias is much reduced. And then if we scale the wind speed, just based on here, the red and blue dots, it's a very similar effect to scaling the freshwater discharge. And if we apply both of those, then we end up with these green dots. So now we've taken it too far. Instead of salinity being slightly over predicted, salinity is slightly under predicted. It's still probably better than the baseline, but it's kind of arguably the same as just scaling either one of the inflows or wind speed together. So we think that scaling the inflows really improves the salinity prediction. And then if we look at dissolved oxygen, we get a similar but a little bit different idea. So here's the baseline. You can see some of these low observed dissolved oxygen values from 2017 are over predicted by the model. The DO is too high. If we scale the discharge, there's still scatter, but the 1-to-1 line is much better. And this kind of collection of points here is now much better in the model. And the same thing is kind of represented over here in the target diagram, where it's tough to see because things start to fall on top of each other. But the baseline is essentially here, where the mouse pointer is. If we scale the inflows, then we make the dissolved oxygen noticeably better. If we scale the wind speed, then we make the dissolved oxygen noticeably worse because we're already a little bit high. We scale the wind speed, we increase the mixing, and we get higher bottom dissolved oxygen, which makes the model actually behave worse. So if we combine the scaling the inflows with scaling the wind speed, then we end up right about where we started. And so that's not really worth it. So after kind of doing this exercise, we go forward with scaling the freshwater inflows. So one of the steps in the pre-processing that we do is we take the NOAA freshwater discharges, and then based on the relationships developed with the watershed model, we scale those inflows before we use them in our model. And we think that that really improves the salinity and the dissolved oxygen that comes out of the model. And anecdotally, I recently saw a report from NOAA where they're looking at kind of a similar thing. If just using the gauge data may be underrepresenting the amount of freshwater inflow that comes in to their model. So it's a little bit of a summary on how the system is set up, how we've adjusted the forcing to not recalibrate the model, but improve the calibration of the model after switching to the CBOF's inputs, and kind of how it's set up. So the next thing that I want to talk about is a little bit on some of the uses. So there's a lot of different uses for something like this. They might not be as obvious as the morning weather, you know, is it going to rain or not? But there are immediate uses that kind of help people plan their day or next day's activity. And one of them is where to fish to avoid low dissolved oxygen conditions. And that seems kind of like a trivial question, like don't go to the main stem of the bay in the summer. But in the main stem of the bay in the summer, there can be productive habitat. It's just high in the water column. And so this is what the fishers have really requested. They want to know the depth to 3 milligrams per liter. And so we developed these plots to visualize where to go in the bay to fish and be in dissolved oxygen that's higher than 3 milligrams per liter. And the image on the left is a colored vertical profile at 4 of the water quality monitoring program stations. And those are marked as the black circles on the plot on the right. And the way we have this is, if you just look at it, the colors are color coded based on dissolved oxygen. Anything less than some orange is less than 3 milligrams per liter. But then the horizontal dashed line provides the depth of the 3 milligram per liter. So you would fish down to that depth, and then you would presumably be in dissolved oxygen conditions that are favorable for striped bass. We also made it so that they have a dissolved oxygen axis on the y-axis, where you can see the vertical profile of dissolved oxygen. You can see it's fairly mixed near the surface and then decreases fairly quickly. They also start to look pretty interesting on some days, as you have kind of a minimum zone in dissolved oxygen that's not actually at the bottom. So here you can see that dissolved oxygen decreases, and then it increases slightly, and then it decreases again towards the bottom. But this is an example of what stakeholders have asked for, and how the first thing that we thought of wasn't as useful to them as what they actually wanted. You know, we were like, here's dissolved oxygen. They're like, no, we really want 3 milligrams per liter. Like, okay, we can do that, and kind of tailored the graphics to be most useful for what the stakeholders were interested in. So another use is oyster aquaculture. So the aquaculture facilities can often have flow-through systems that they can turn on and off. And if the water chemistry is wrong, then the oyster spat will dissolve, the shells for the baby oysters will dissolve, and obviously that's a bad thing. And so we're working with some of the oyster aquaculture to figure out what and where to provide them to help them kind of plan the next couple days. If there's a big rainstorm and the salinity is going to change drastically right next to them or something like that, then they may be able to preemptively close their flow-through systems if it's a stage in the life cycle where they need to do that. And so this is the start of what we're looking to provide. Still getting feedback on this type of thing, but it's essentially time series of surface and bottom salinity and surface and bottom pH. So the blue line is the model prediction and the model forecast. So you can see I grabbed these from somewhere in the morning on July 6th. And then in the background is also based kind of the average, the long-term average in black, and plus or minus 1 standard deviation in gray from the water quality monitoring program at the same location. So it gives you a couple pieces of information. One is what the forecasted conditions are going to be, and 2 is how that relates to the long-term data. Kind of 2 different ways of looking at it. Are we going to be outside the range of what we'd expect based on the long-term data? And what are the actual values going to be? And then we've also put quite a bit of effort into looking at summer hypoxia. And so one of the cool things that the forecast model does is that it really allows us to track the hypoxia throughout the summer and see how it's progressing, and either how it responds to heat waves or large storms that come through the bay, things like that. And then we use it for an end of year dead zone report, kind of summarizing how did hypoxia this year compare to years past. And we've, over the last few years, we've developed a few graphics that are somewhat succinct and somewhat complicated to put online to be able to visualize this in real time. And the one on the left is kind of the main one that shows how hypoxia has been this year. So 2021 is the shaded blue on the top and on the bottom. And then each of the last 5 years are the single line. So we can compare this year to kind of the recent past. And this top panel shows the instantaneous hypoxic volume on any given day. So it's essentially tracking the severity of hypoxia on any given day. In the volume of water, kilometers cubed, less than 2 milligrams per liter. And then the bottom panel is what we call the total annual hypoxic volume. And the units of that is a little tricky in that it's kilometer cubed days. And so for each 1 kilometer cubed for 1 day on the top panel, that all gets summed up and then added to the bottom panel. And so the bottom panel is tracking the cumulative hypoxia over the course of the summer. So we can see that 2021 is trending much worse than 2019 and somewhere in line with the previous 5 years. We'll have to wait and see how it stacks up in the end. So it's not, so far 2021 isn't tracking abnormally low and 2021 isn't tracking abnormally high. It's just kind of in the range that we would expect based on the recent past. If we look at that compared to the data, we get a little bit of a different story. And I'll get into that a little bit on the next slide too. So this is, here the shading is the same daily hypoxic volume as over here. But now it's broken out based on Maryland waters, Virginia waters, and Potomac River. And then when the water quality monitoring program goes out and collects their vertical profiles, they're providing those to us over the summer so that we can make a data-based estimate of hypoxic volume. So essentially interpolate the data in space and get an estimate of hypoxia. And if you look at the data, this year is stacking up to so far be very atypical, where you have hypoxia in May, and then very little or nearly the same amount of hypoxia in June. And we don't have late June or July, so it's just the first June cruise so far. But seasonally, you would expect hypoxia to increase from May into June. That's what the model's doing. The model shows a down dip here, right when this data was collected. It doesn't come down as far as the data. So the data is suggesting the model may be over predicting hypoxia a little bit here. But the pattern matches where you have increase in hypoxia and then a decrease in hypoxia right at this data collection. So one of the things that I think is cool about kind of models in general and this forecast model is that we can dig around in the model output and kind of things that we're already creating for the forecast system and try and understand the data better. Because I believe this is one of the best June hypoxias like on record. It's very low. And so why is that? Is it just great conditions? Is it an artifact of good conditions and sampling? Like, what is it? So these are two other types of plots that we put out online that are, again, updated every day on that web page. And so here, the blue line is the modeled dissolved oxygen as a continuous line. And the gray dots are the water quality monitoring program data. LE 2.3 is here at the mouth of the Potomac, and CB 5.1 is here in the middle of the bay. And you can see that the data dots are every week or every month, sometimes of the year, every 2 weeks as we get into the summer. And if we just look at the data dots for the dissolved oxygen concentration, again, it's kind of atypical that from May to June, you would have an increase in dissolved oxygen at these main stem locations that are generally on their way to hypoxic this time of year. But if we overlay those on what the model is suggesting, the values may not match exactly. So at LE 2.3, the model accurately captures dissolved oxygen in May, and then it's a little low in June. But we can see that from May, on average, from May to June, dissolved oxygen is decreasing in the model. And that coincident with the data collection location, there's actually an uptick in dissolved oxygen, be it from cool temperatures, wind mixing, not sure. But one of these kind of 2-week cycles, weekly cycles in dissolved oxygen, is a peak when the data was collected. If we look at CB 5.1 here in the middle of the bay, we see a similar thing. The model is suggesting that the May data collection occurred at kind of a local minimum in dissolved oxygen concentration there, and that the June data collection occurred at kind of a local maximum in the dissolved oxygen concentration there. Yet if you follow the May to like the April to July progression, the model is suggesting that this year is very closely following the long-term average. And so it kind of looks like just the coincidence of when the data collection happens leads to the similarity in the May and June hypoxic volume estimates. Another thing that I think is really interesting from these plots that I was just kind of noticing yesterday is that if you look at the variability in the blue line, the model dissolved oxygen, in relation to the plus and minus 1 standard deviation of the data, then the model blue line essentially sets your plus and minus 1 standard deviation in the data, at least at these 2 stations for this time period. So you may be able to start using these model results to better understand the variability that's seen in the data itself. So is variability in the data really representative of very different dissolved oxygen conditions or very similar dissolved oxygen conditions? Or is the variability that's seen in the long-term data representative of the week to 2-week cycles or variability that's in the dissolved oxygen data? Like, is the variability based on annual difference in dissolved oxygen, or is the variability in the data just because the data collection is infrequent and somewhat randomly captures local minimums, local maximums, and the variability is kind of set by that weekly to 2-week to monthly, like short-term variability in the data and not necessarily interannual. I think one of the things that the model can be used for is really kind of digging into the data. Like, how do we compare, how do we add the data and the model and come up with understandings of both that are better than if we just used one or the other? And so that's something that at least I'm interested in, and I use the online kind of forecast to look at that type of thing throughout the summer. Another one is kind of along the same thread, another use. We can use this type of model to really plan for data collection. So we've had a recent short discussion just through email, and there was an intermediary to me. But the idea was that a scientist wants to go out and collect data, but they want to ensure that they're going to be in anoxic conditions or as close as they can get. And they were wondering if the forecast model can help them with that. And I think the answer is yes. If there's some flexibility to the cruise location, when it goes or kind of where exactly in the bay they go, then they can look at the forecasts a few days out, a week out, a day out, to try and ensure that something hasn't changed, be it a wind event, a lot of mixing, cooling, where they were planning to go is still anoxic. And so again, from kind of a science standpoint, if there's some flexibility in where the sampling occurs, then the forecast could just confirm that that sampling location is still correct. It's still applicable for what the study focus is. So that's kind of a summary of some of the uses and some of the things that we think is neat to use the forecast system for. And like I said at the beginning, we've really been kind of continually expanding and improving the forecasts. And so I wanted to talk a little bit about next steps and kind of where we think this is going. So one of the next steps is really lengthening the duration of the forecasts. And this has started. So we're working towards trying to lengthen to a 5-day forecast, make it a little bit more relevant than just 2 days out. The thing about that is that because CBOFs is only 2 days, we essentially have to go away from leveraging the work that NOAA was doing and do all of that effort ourselves. And so that's started, but we're not there yet. We have some more funded cool next steps. So it would be adding HABs and Vibrio probability to the forecast. So it's the probability of encountering HABs or Vibrio throughout the Chesapeake Bay. And then as part of that, we're going to try a little prototype of like automated email alerts. So if HAB reaches some threshold or Vibrio reaches some threshold somewhere, the forecast system would automatically send out email alerts. And then other things that we have planned that are in various stages of subjective funding or hopefully funding coming is real-time wind waves through coupling to the SWAN model. So ROMS is already coupled to SWAN, and so we would try to leverage that to run real-time wind waves as well. And then spatially distributing the freshwater inflows. So currently, all of the freshwater inflow comes in at the head of the rivers, when in reality, that's not where all of the freshwater inflow enters the bay. And so we would work towards distributing those freshwater inflows away from the heads and kind of better distribute them around the margin of the bay. And some of that work has already been done by Pierre, but it hasn't been incorporated into the forecast system. And then adding detailed real-time model data comparison. So there's CBEFs or CBIBs buoys and other real-time data that's available that we could add a kind of a web page detailing kind of this is any biases in the model as of today. This is how the model's been doing seasonally. Where's it at? And then assimilate bottom dissolved oxygen. So we found through previous work that the model doesn't really respond to assimilating surface dissolved oxygen, which is the easy data to come up with. But it does respond, and we can increase model scale if we have bottom dissolved oxygen. And so if that data becomes available, the bottom dissolved oxygen, it's something that we would like to work towards assimilating into the model. And then also real-time habitat suitability maps for select species. So what's the suitability of the habitat throughout the summer as temperature changes, as dissolved oxygen changes, as salinity changes, that type of thing. So as a quick summary, because I have some discussion questions at the end, and one of them kind of focuses on this. For lengthening the duration of the forecast, the plan is for 5 days. And like I said, that requires moving away from the CBOFs inputs, which are only 2 days. So we instead have to go back to the initial sources. But it also may involve combining inputs from multiple sources. So like meteorology, we'd like to continue to use the high resolution NAM, but it doesn't go to 5 days. And so we would then have to combine that with something like global forecast system meteorology for the end of the forecast. Non-tidal water levels we would take from another forecast product. I believe it's different than what CBOFs is using, but it would cover the full 5 days. And then we also will need Atlantic Ocean open boundary conditions for things like temperature and salinity. So what we've been considering is using the Doppio nowcast forecast output for the time period that's available, and then using the global real-time ocean forecast system. So kind of combining another Mark-who's forecast product with something else to get to the 5 days. And then for freshwater inflows, we're just planning on using the scaled USGS data like we do currently, and probably holding it constant for the last part of the forecast or trending towards some sort of an average. And we've talked about using National Weather Model forecast flows if that ends up working out. So in summary, the Chesapeake Bay Environmental Forecast System is a completely automated real-time forecasting system based on three-dimensional hydrodynamic and biogeochemical models. And it was recently revised, starting in February this year, to use a higher resolution model grid. And so it's much higher resolution than it was up until just February. And then we've continuously refined the online visualizations based on stakeholder feedback. And these are available on the VIMS website and on the Maracus Chesapeake Bay Oceans map as kind of more of an interactive map. So the VIMS website essentially has our stakeholder tailored graphics, and the Maracus Oceans map page has more of a interactive, clickable, compare to data, that type of thing. And it's really been used by a range of kind of the general public and scientific stakeholders, from fisheries to aquaculture, hypoxia, and water temperature. And we work towards continually revising, updating, and expanding it. And kind of along that lines, and while we had people on the phone, I was told that there might be time for discussion and questions and things. So I have some possible discussion questions. I would say we open it up for anyone who has questions. And then if there's still time, I just have some general questions for people who might have answers. Like, are there any lessons learned? Has anyone else done automated alerts? And maybe we could connect offline and kind of talk about that, kind of lessons learned. Are there any other sources of inputs that we should really consider looking at 5-day forecasts? Should we use something like the Doppio water levels, low pass filtrum, and use those for non-tidal open boundary water levels? Because that would be another way to use similar products for different portions of our forecasting. So for that, I think I'm gonna wrap it up. If anyone has questions, let's see, can I?
Thank you so much, Aaron. Like you said, we'll open things up for questions. I'm seeing a couple in the chat. What I'm seeing, can you talk a bit about the model CalVal for shallow regions?
I can talk a bit, not a lot. That's a question we get a lot, is that we're focused on deep main stem, and a lot of the bay is not necessarily deep main stem. I think that as we move forward with this high resolution model, there will be more and more focus on the shallows. And so if we go back, so this example here is kind of off to the side in the York, and in the model that we used up until about February this year, it just didn't, you might get the average, the long-term average right. It didn't necessarily resolve it. And so one of the reasons I'm going to this higher resolution model is that we can definitely start to look more at the shallows and be more applicable to things in the tributaries and more of the margins of the bay.
Okay. I'm seeing.
It looks like Carl has his hand raised. Yeah.
Yep.
Yeah.
Carl, you can go ahead and unmute and ask your question.
Can you hear me?
Yep.
Okay, great. Boy, Aaron, that was really great talk. I've been following you work on this with Margie for a long time, and it just keeps getting better and better. I think that example of the ups and downs and how the timing of the cruises makes so much difference would be a wonderful thing to present to the modeling work group at Chesapeake Bay program. Maybe Margie and you could talk about that. But I thought I wanted to comment on the deep irony of this being down at this moment. And I was thinking that Maracus might provide a great opportunity to have a live forecast accessible even when VIMS goes down. And I was wondering, we've been thinking about this a little bit, where I do the observing system support indirectly. I supervise the data scientist who runs the VCOS, the Virginia Estuarine Coastal Observing System. And we've had some frustrations with VIMS IT resiliency and have been playing around with using cloud services for the computational part. And I wonder if it might make sense in the long term to have the computational part of CBEFs be in the cloud. Of course, it would still feed to the VIMS website because that's a very important thing for many reasons for VIMS to have the visibility there. And that, of course, would still go down if there was a storm. I mean, this was a big deal. It wasn't a minor thing. There were tornado watches, and the power only just came on now. Anyway, so there's some serious things that happened at VIMS, but these things do happen occasionally, probably at least a couple times a year at VIMS. And maybe the cloud could support the computation that would then feed the images that you use at VIMS, but then it also would provide a path for Maracus to pick up the computations and serve them on a more resilient system so that there would still be an access to this great information no matter what was happening at VIMS.
Yes. So let me jump in. We've considered the cloud as kind of a test case. We considered like doing a test case through, I believe it was Amazon Web Service. And the issue became that the cost was so expensive that it was just like no go. The test case, like the costs we came up with for a test case of like running, it was for running CBOFs, not this one, but for helping NOAA calibrate CBOFs for dissolved oxygen on the cloud. And the costs we came up with simply to like tune the one-term respiration rate were just like a no-go. The computing cost in the cloud was like really high compared to running at VIMS where the computer's already there, or the NOAA running it on their computers are already there.
I wonder if there's a way to get a bulk discount rate. I mean, I know RPS has been doing stuff in the cloud in support of some of our services.
Yeah, we were doing this through RPS. And so they were costing out how much it would cost to run in the cloud. And the thought was, like, initially this conversation came about because they were doing 6 hour stuff for NOAA on their 6 hourly forecast cycle. And I said that, to really calibrate, we'd need to do 2 different years, so it wasn't calibrated to simply one set of environmental conditions, and we would need to run the whole year, and that type of thing. And that took the 6 hour cost and multiplied it by however many 6 hours there are in 2 years, and the whole thing like skyrocketed. Not to the completely obscene point, but to the point that as a test case, no one, like, it kind of was dead in the water.
Gotcha. Okay.
Or on
Yep.
cloud.
Can I just say one thing, so that although the power is back on, I guess, at VIMS, but the internet is not working yet because we don't have it up. But all of these maps are on the Maracus site right now, so you can go there, and they are all showing beautifully. So that's another reason why it's nice to have 2 sources have them shown in 2 places, both on the Maracus Oceans Map portal and then also on the VIMS website, because it's not often. And it really has gone down at most 2 days a year, really, on average, even though we're on this coastal, where we're running on the coastal Gloucester Point campus, it goes to actually that campus ends up going down less than the main campus at Williamsburg. So yeah, anyway, it was unfortunate, but glad you had the images.
So real quick, there's a lot of questions in the chat that I'm not going to be able to keep up with. Like, can we save the chat so that I can go back to it?
Absolutely.
Or do I have to try and copy and paste?
No, we'll save the chat, and you can, we'll send it out to you, and we can, seems like there's a lot of interest in this. We can certainly transcribe questions, and if we need to convene another meeting as a follow-up, that would be fine too.
Okay,
A couple
thanks.
other hands raised.
Hey, Garrett's here. I just want to say something to that last point. So, Aaron, thank you very much for this presentation, and both to Aaron and Margie. Obviously, Carl raises an important point, and while it may be difficult at this very moment in time to envision that, I mean, increasingly operating in the cloud is becoming more important. IUCE has been funding, as you know, efforts to try to investigate and develop that more. And I think I think we ought to keep at this and take a look. I mean, we learned the hard way, I think, during Sandy, when a lot of systems went down. I think, just letting servers run on the coast until, the power surge fried them, and we didn't have backup systems, and people, it's the dilemma of trying to keep it going so that your stakeholders have access to it until the very last second, and then we didn't have backup systems. So I think we've learned a lot of lessons over the years, and others here too, including John, are familiar with the efforts. So I think we just ought to, we ought to discuss, we want to continue the discussion, because I think, there may be opportunities to highlight the challenge and seek augmented funding in some ways, or supports to make that happen. Because I mean, obviously we want to approximate or approach operational status like, our operational partners do, and they can only rely on us if that's, if we're able to deliver. So, but thank you. Really appreciate your time.
Looks like, John, do you have a question? Your hand is raised.
Thanks, Aaron. That was a really great effort that you've put together here. I've got a number of sort of comments and thoughts about the 5-day forecasting issue, which is something we've wondered about ourselves with Doppio. And in principle, we could do it. We've got long enough forecast open boundary conditions from Mercator Ocean. We could roll the NAM or HRRR forecast over to GFS for days 4 and 5. The only limiting thing really is the river flows. And I wonder if you've thought about this, because we've thought about this, just building a simple autoregressive predictive model to get those last couple of days to get out to 4 and 5. Because, with the river flow inputs being way up at the top of the tributaries, the transport lag for those is, it's pretty long. They're not going to have a huge impact on your forecast in the main stem of the bay at day 4 and 5. And then when the data comes in, you can just, you'll be rerunning the analysis. So just some thoughts there.
Yeah. I think for the tributary parts, one of the downsides is that by day 5, if an aquaculture is like planning on using it, then, and the river, like if the nowcast is for really high inflows, then by day 5, we can't just keep pumping if that's not the way it's going to be. And so we've thought a little bit about it, but in the actual like getting it running part, the meteorology and the open boundaries are the important part. And then rivers, we may just kind of trend towards some average value or at some trend, either up or down, just at some rate to start with.
So if you look at, if you take a typical river discharge time series, you'll get a large peak when there's a rain event, and then it kind of decays down, right? It's the kind of thing that is very well predicted by a first order autoregressive model. And what that's going to do over 4 or 5 days timescale is kind of revert to climatology, but retain some memory of those discharge events. So I think it could be, reasonably skillful. Certainly, something we could look at collectively. I don't want to become a hydrologist. I've already had to become a biogeochemist and a meteorologist. I want to stop there. But it's something we could look at. Similarly, if you just wanted to apply an autoregressive model to the Doppio open boundary conditions, I think that would be perfectly acceptable to take you from days 3 through 4 and 5, because temperature and salinity are moving slowly, and the subtidal variability sea level similarly.
Okay.
Yes, we can. I think we're almost at time. Does anybody have any last questions? I know there's some in the chat that we haven't answered, but we'll, like I said, respond to those in writing, or Aaron will respond to those in writing. We'll send them out to this group and others who were unable to join but interested. But last call for questions.
Hi, this is Hugh at Rutgers. Hey, Aaron, why is the Potomac broken out separately when you're looking at the state waters?
Because it's relatively large in terms of the amount of hypoxia. It's not as large as Maryland, and it's bigger than Virginia.
Okay.
And we've had a lot of conversation with different Maryland folks and Virginia folks and Chesapeake Bay program folks about ways to report hypoxia. Do you report Maryland? Do you report Virginia? Do you report the whole thing? Do you look at tributaries? Do you just look at main stem? And we've pulled out the Maryland, Virginia, Potomac as kind of just a little bit more information that was feeding kind of those discussions on what's on how do we standardize reporting of hypoxia? Not necessarily because one area is more or less important than the other, but just kind of a little bit of extra information that was feeding into those discussions of what's the right way to report this.
Okay.
Or what's
Gotcha.
the right way to standardize how we all report this.
Okay. Thanks.
All right, well, thank you so much again, Erin. This was a fabulous talk. Hang on a second, I'm sorry. We have a few other speakers lined up for the summer, and we will send out that login information next week. If you or someone you know are interested in doing a science talk, please contact Mary Ford at mary@maricus.org, and we will get you on the schedule. Thank you so much. Have a great day.
Thanks, everybody.
Thanks, Aaron.
Thanks, everyone.